This is AS Pure Notes, and we've just started Unit 4 and we're looking at functions. It says below, draw a graph for y equals x squared for minus 4 to 4. So I'm going to set this one up now. So my scale along the bottom, that's obviously going to be 0, 1, 2, 3, 4. That's my x-axis, minus 1, minus 2, minus 3, minus 4. And then go up here then in ones, obviously, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that then is my y-axis. So I want to plot the points for y equals x squared. So first of all, if we go for 0, 0 squared is 0, so that would be a point on it. 1 squared is 1, 2 squared is 4, 3 squared is 9, and 4 squared is 16. Minus 1 squared is 1, minus 2 squared is 4, minus 3 squared is 9, minus 4 squared is 16 as well. So I'm going to join that together as best as I can. A wiggly line, but you get the idea. So that's not bad, not great. Now on separate sheets, sketch the graphs of the following, choosing two values of A for each type. Consider the coordinates of the original point and the new points. Can you see a connection? So you need to go away and try that. If you have a load of different copies of this here, this is the best way to do it. And what you'll find is if you plot this, say we plot f of x plus 2, what does that mean? F of x plus 2, if we're above 1, if f of x is y equals x squared, then we're going to plot y equals x squared plus 2. And what you'll find is it's exactly the same graph, exactly the same shape, however it's moved up 2. So everything's kind of been moved up by 2 coordinates. For this one here, e.g. f of x plus 3, so we would be anytime we see an x, we change it for an x plus 3. So if we plot that one, we need to do FOIL and multiply it out and try and plot it. But what this one actually does is moves it 3 along the x-axis, only the wrong way. So actually this bit here, which is the turning point, would now be over here. So this one here moves the graph across this way. A f of x, again if I pick a wee example, for example 2 f of x, what that does is stretch everything twice as far away from the x-axis as it normally is. So instead of being the point 1, 1, it would be the point 1, 2. Instead of being 2, 4, it would be 2, 8. And so everything stretches up that way. And then the final one, again it's a bit of a strange one, for whenever it's dealing with things that are moving along the x-axis, things are a bit more odd. This squeezes everything in 3 times closer to the y-axis. So it looks actually, the graphs actually look quite similar for this one and this one, but it's evaluated in a different way. So everything squeezes in then 3 times as close. If you turn over to the next page, that's kind of a, I guess, a more way of explaining each of those kind of 4 things. It's much better seen in the examples, and hopefully then if you watch the next video in the examples, that'll make a lot more sense. Vertical translations, y equals f of x plus a, shifts the graph vertically by a units. That's what we said, f of x plus 2 moves everything up 2. F of x minus 3 would move everything down 3. Horizontal translation, f of x plus a, shifts the graph horizontally by a units. Left, if a is positive, so that way, if a is positive, and right, if a is negative. Y equals a f of x is a vertical stretch. So everything on the x-axis, let's go back to our graph, stays as it is, but everything else stretches up by a factor of a. If a is less than 1, obviously it's still a factor of a, like a half or something like that, then it would squeeze it down. And then a horizontal is kind of like a compression, so it's horizontal by a scale factor of 1 over a. So just kind of what I said, say it was f of 2x, I've written f of 3x here, but it was f of 2x, everything would squeeze in twice as close as it is towards the y-axis. So that's generally the 4 different graph transformations that you need to be able to deal with. If you watch the next video, we'll give you a much better idea then of The sort of example you would see in a past paper question.